So now that we have understood how spherical mirrors are made, now we need to understand reflection of light from spherical mirrors. For that, what we need to do is, we need to incident some parallel rays of light on both the mirrors. So let us incident parallel rays of light on a convex mirror. Now, due to the shape of this mirror, what do you think will happen? This parallel ray of light, will it get reflected in the upward direction or downward direction? Obviously, upward direction. Similarly, this ray of light would get reflected in the downward direction, and this particular ray will get reflected back in the same direction. Now, if you see properly, all the three rays of light that you see over here, are they coming towards each other or moving away from each other? Away from each other, right? This in technical terms is called as diverging. So convex mirrors are diverging mirrors. Similarly, we'll incident some parallel rays of light on a concave mirror. Now, as you can see, we are incidenting parallel rays of light. Now, this particular ray of light will get reflected in the downward direction, this ray in the upward direction, and this particular ray will get reflected back. Now, are these rays coming towards each other or moving away from each other? Coming towards each other, right? This in technical terms is called as converging. That means concave mirrors are converging mirrors. Convex mirrors are diverging mirrors. Concave mirrors are converging mirrors. So now we have understood how reflection of light takes place from spherical mirrors. Now we need to understand certain common terms. Why common terms? Because they are common for both the spherical mirrors. One question. What do we want to make spherical mirrors? We want a transparent glass sphere. So we have a transparent glass sphere and we can make two types of mirrors, convex mirrors and concave mirrors. We also know for a fact that every sphere will have a center. The center that we have over here is called as the center of curvature. Now, to understand the center of curvature or to define the center of curvature, we need to do something. What we need to do right now is we need to have something which looks like a plane mirror. So let us have something that looks like a plane mirror. So here I have this. This looks like a plane mirror, right? Now, what do I need to do in order to draw a normal at this surface? I need to draw perpendicular. We know that a normal is nothing but an imaginary perpendicular, right? So what I'm going to do right now is, instead of drawing a normal, I'm going to have this. So here you can see what we have over here. These lines look like normals, right? Now what we need to do is we need to understand something. This looks like a plane mirror, right? And we have normals over here. Now what I'm going to do is I'm going to bend this particular thing. So when I bend it inward, you can see that all the normals are converging at one point, right? And this particular point that you see where the normals are converging, that particular point is called as the center of curvature. So the normal from a concave mirror converge at a point, and that point is called as the center of curvature. Similarly, what I'll do right now is I'll curve it outwards. So when I curve it outwards, again you can see that the normals are converging at one point, and this point is called as the center of curvature. So right now what we understood is that the center of curvature is nothing but a point where the normals converge. So we have understood center of curvature. So in simple words, center of curvature is nothing but the center of a sphere. Now similarly, we also have a center of the spherical mirror, and that is denoted by capital P, and we call it as the pole. So center of curvature is the center of the sphere, but pole is the center of the spherical mirror. So we have learned two terms, center of curvature and pole. Now if we draw a horizontal imaginary line passing through the center of curvature and the pole, that particular line or imaginary line or horizontal line is called as the principal axis of a mirror. So the horizontal line which passes through the center of curvature and the pole is called the principal axis of a mirror. Now, one easy question. What is the distance between the center and the circumference of a circle called as? Radius, right? Similarly, we have radius of curvature in spherical mirrors, and that is nothing but the distance between the center of curvature and the pole, because this point pole P is on the circumference. So the distance between the center of curvature and the pole is called as the radius of curvature. Now, you might have heard teachers tell you, please concentrate over here, please focus over here. So by this, what they actually mean is they want everybody's attention to come at one point. And in this chapter, we also have something called as the principal focus. Now we'll define principal focus of a concave mirror and a convex mirror in two different times. Why? Let us try and understand this. So first of all, to understand the principal focus of a concave mirror, let us have a concave mirror. Now, what we are going to do is, we are going to consider an object which is placed at a particular distance, far away distance. That means the rays of light are going to be parallel. So we have certain parallel rays of light getting incident on a concave mirror. And we know that concave mirrors are converging mirrors. Now, since they are going to converge, these rays after reflection are going to meet at one point. And this particular point where the rays meet after reflection is called as the principal focus of a concave mirror. So what is happening? The rays coming from a distant object parallel to the concave mirror will converge at a point, and this particular point is called as the principal focus, denoted by capital F, of a concave mirror. Now what we need to understand over here is that the rays of light are actually meeting, and whenever the rays of light actually meet, such type of a focus is called as a real focus. So concave mirrors have real focus. Now let's understand the principal focus of a convex mirror. For that, we'll have a convex mirror in front of us, and we'll keep an object at a distance, and the rays of light would be parallel to each other. So we have certain rays of light which are parallel to each other, and we know that a convex mirror is a diverging mirror. So the rays of light are going to diverge. Now, we know that they are diverging. But if somebody stands over here and looks at this ray would appear to be coming from a point somewhere over here. Similarly, all the rays would appear to come from a point which is somewhere over here. And this point, where the rays are appearing to meet, right? They are appearing to meet. That particular point is called as the principal focus of a convex mirror. But you might say, sir, this mirror, that is a convex mirror, is a diverging mirror. So can we say that these rays are appearing to diverge from this point? They are actually diverging from these points, right? But they are appearing to diverge from which point? This point. So how will you define? The parallel rays appear to diverge after reflection. If we extend the reflected rays backwards, they meet at F, and that is the principal focus of a convex mirror. One question: are the rays of light actually meeting? No, they are appearing to meet. And whenever the rays of light appear to meet, such a focus is called as a virtual focus. So concave mirrors have real focus, convex mirrors have virtual focus. Now, one last common term that we need to understand is called as the focal length. And that is nothing but the distance between the pole and the focus. And focal length is denoted by small letter f. You also need to remember something, that the distance between the pole and the focus is always equal to the distance between the focus and the center of curvature. So, if this distance is small f, what would this distance be? Small f, right? But we also know for a fact that the distance between the center of curvature and the pole is nothing but the radius of curvature. So can I simply say that this capital R is nothing but f plus f, and f plus f becomes 2f. So we have R is equal to 2f. Also, we can find the relation by shifting 2 on the other side. So we get R upon 2 is equal to f. So f is equal to R upon 2. In simple terms, we can say that focal length is nothing but half of the radius of curvature. So focal length is nothing but half of the radius of curvature. So these are the common terms that we have understood. So to summarize it, we have learnt how reflection takes place from spherical mirrors, and we have learned certain common terms. Center of curvature, denoted by capital C, is nothing but the center of the sphere. Or we can say that where the normals converge. And also we have studied pole, that is nothing but the center of the spherical mirror, denoted by capital P. The straight line or the horizontal straight line passing through the center of curvature and the pole is called as the principal axis. Similarly, the distance between the center of curvature and the pole is called as the radius of curvature. Then we understood the principal focus of a concave mirror and a convex mirror. In principal focus of a concave mirror, we know that the rays of light actually meet at the focus. That means it is a real focus. And in a convex mirror, we know that the rays of light appear to meet at the focus, and that focus is a virtual focus. And finally, focal length is nothing but the distance between the pole and the focus, and we have found a relation between the focal length and the radius of curvature, which is focal length is half of the radius of curvature.
And yes, please do not forget to like, share, subscribe, and press the bell icon.